Welcome back. I'm glad that we have a bunch of people here again. So, as you'll recall, Dennis was speaking yesterday about the definitions of spherical intrinsic volumes and the basic ideas from spherical orbital geometry. Today's going to be talking more about the kinematic formula and some interesting applications in the study of semi-definite programs.
Thank you all for coming back. So today I'm going to talk about basically some specific kinds of cones which are very interesting, the symmetric cones, and basically we want to shed some light on the question: what's the probability that the solution of a random semi-definite program has rank R? So when you have a semi-definite program, then the solution is some matrix, right? And it has some rank, and this rank has some, well, it cannot have an arbitrary rank, but and then we ask about what's the probability that we have solution, that solution has rank 1 or 2, and we want to shed some light on this question today. So well, first of all, I have to talk about what I understand under a random convex program, because I need to specify some model to actually make sense to this question that I just formulated. And well, you will see that in some way this will lead us to a certain localization of intrinsic volumes. And so then we will see a certain implication of the kinematic formula to actually get an answer to this question. And well, after that we will have a closer look at kinematic formulas, and the actual way to understand them, in my opinion, is to look at the support measures. And well, we have some lattice structure that we will see. And then at the end, I will give some formulas for the semi-definite cone, and so it's a local program. Okay, let's start with a random convex program. So first of all, what's a regular cone? Well, understand under a regular cone just a closed convex cone, such that both the interior of the cone itself as well as the interior of its dual is not empty, right? So think about C being the cone of the positive orthant, or the cone of positive semi-definite matrices. And well, and so what I understand under a convex program with reference cone C is the following. So assume that we have as input some vectors Z and A1 to AM, and some real numbers B1 to BM. Then we have some linear function. So Z is a linear function that we want to maximize, say, and we have some constraints on this X, and some linear constraints, and then this convexity constraint. And so you see, if you put for C the positive orthant, then this just means that X should be negative coordinate-wise, and then you get linear programming. If you plug in the cone of positive semi-definite matrices, then you get semi-definite programming. And so this is sort of like a general formulation of this convex programming. Okay, now what I understand under a random convex program is sort of like the simplest form of a random convex program. So we say that these vectors Z and A1 to AM are IID standard norm. Right? So I mean, it's not a very realistic model, but it's sort of like the easiest one that we want to consider. And so this B1 to BM, they can actually be arbitrary fixed constants, such that the vector is not the zero vector. Right? So there was some comment of Mike that in the paper we say that we also take B1 to BM standard normal, but we don't need this. So it's enough to just take some fixed constant for this. All right. So this is our random model for a convex program. And okay. So now if you want to solve this, then first of all we need some definition. So the set of inputs which satisfy the constraints, so this f of Cp is just the set of inputs over which we want to maximize our linear function. This is called the feasible set. So and then if we maximize this linear function as Z, then we get a certain value. This value can be infinity. Or it can be this feasible set can also be empty. But anyway, so this value of Cp is the supremum over the feasible set here. And so then we have the solution set, which are those inputs which actually achieve this maximum value. Right, and okay, now we can have 3 possible outcomes. First of all, the set of constraints can be empty. Right? Then we say that the CP is infeasible. And well, we can have that the value is actually infinity, then the CP is unbounded. And then the third, and this is really the interesting case, is that we have a non-empty set of feasible inputs, and the value, well, the value of the program is actually not infinite, so it's a bounded thing. And so one can show, it's not hard to show that in this case, almost surely the solution set is exactly one element. Right? So under our random model that we had before, then we can say that with probability 1, we actually have a unique solution to our Convex program. All right. So now, we'll see later how this actually follows from the kinematic formula, but I just wanted to mention that it is not too hard to show that one can characterize these the probabilities of these outcomes in terms of the intrinsic volumes. So the probability that our Convex program is infeasible is just the sum of the intrinsic volumes from 0 to m-1. So remember that m is the number of constraints that we have. So it's, if you think of it geometrically, then m is the codimension of the subspace that you're taking. And yeah, so the probability that the Convex program is feasible bounded is exactly the mth intrinsic volume, and so is the third one, the remaining intrinsic volume sometime. So yeah, so let's specialize to the case of linear programming. We've seen in the first talk what the intrinsic volumes are. It's just the symmetric binomial distribution, and so we get these nice probabilities. And actually, I mean, linear programming is sort of like, there are several ways to look at linear programming, and so these probabilities have actually been achieved by several people. Under them is Ada Beringer, Sporishev, and also Chunga-Kuka, and so there are several ways to actually prove these probabilities, but they sort of fall out of this theory of intrinsic volumes, and they follow from the kinematic formulas. And we will see later how this actually works. Right, so, and, well, just to have a picture, so here we have the... Say it again? Sorry.
Yeah. On your previous slide?
Yeah.
So, in the linear programming context, the equivalent of the question you're asking is what is the support of the solution?
Well, in the linear programming, so the rank in the linear programming it doesn't make too much sense because the solution is attained at some basis. So the basis vectors will be
So there's no natural way of having a basis and talking about the support on that basis. Is that what you're saying?
Well, the thing is the analog of the rank in the linear programming case would be how many of the coefficients are non-zero.
Right.
And with probability 1, you will have, I think, m or n minus m. So non-zero, I think m. Because
but what is the natural basis in which this would be true? That's what I'm wondering. So, in other words, is there an analog here, and what is the natural basis in which you would look for a sparse solution?
So the thing is that well, if you think of it in the linear programming case, you get some, well, the feasible set is some polyhedron, and then the maximum is attained at some extreme point, right? And this is satisfied by some basis vectors. And well, these basis, so you actually can write this in terms of the basis, and so the number of non-zero elements will be exactly n with probability 1 if you have this random model. And so yes, so there's no.
No, what I'm wondering is, what is the natural basis here? When you say basis, I mean, there is no. Is there a natural basis?
But then what do you mean by basis?
No, because you see, I mean, rank is something that has nothing to do with, when you look in the matrix case, right, there's no, rank is rank. Right, I mean, there's no, but when you talk about the support or the number of non-zero entries in a vector, it depends on the basis, right?
Can I see what I mean? But
anyway, maybe I was just wondering if there was an analog to the problem you're looking at here, and I'm not clear what the analog is. That's what I was.
Let me just hope that there's some correlation between things that I'm not quite understanding. So there are two models you talked about, the semi-definite and the LP, and I'm not quite sure what the probability model is you're using for generating an LP. So maybe you can just say what the process is.
well, you basically choose. Okay. If you think of it in terms of a matrix, then you take the matrix, just a Gaussian matrix. So you take the entries of the matrix to be ID standard normal.
So okay, two things here. C, what's C?
C is the linear function that you take, and this is also a Gaussian vector, Gaussian random
C is
vector.
not a linear function.
So you basically take a uniformly random direction.
C is not a linear function. C is your cone.
Sorry, Z. Sorry, and C is positive order.
C is the positive order.
Right.
Okay. And you ran Rn, we have M constraints, A sub I, B sub I, which are just Gaussian. Well, I don't care about the B sub I's so much.
No, the B is just
Yeah, right.
Yeah.
But the A sub I's are Gaussian IID.
Right. So it's not a very sort of useful model for applications, but it's sort of like the easiest model that you could think of.
Right. And you're saying that in this model, there's a sparsity statement that you can make, which, yeah, okay, I understand.
Yeah.
How long does it, I guess what's confusing me a little bit is that this is going to be often infeasible. So maybe you talked about
Right,
that,
right.
But
That's true. So if you think of it in high dimension, then it's either infeasible or unbounded with very high probability. Yeah, that's true.
and so this, okay, now maybe go back to where the results were, and you're telling us what those probabilities are actually now?
Yeah. So this is the point. So here for the LP case, this is exactly this one. So you see in high dimension, with very high probabilities, it's either infeasible or unbounded.
As there's only a single binomial coefficient that
Right.
falls.
Right.
Ah, right.
That's true. So it's not a very good model, but it's sort of. Right, I have always this picture in mind. If you think about the discrete binomial distribution, then you have the left tail gives you the probability of infeasibility, the right tail gives you the unboundedness, and sort of like this one guy gives you the probability that you actually end up with a feasible and bounded linear program. Right.
And
yes.
just if you don't mind handling random shunting. So how close is this kind of work to random KSAT? So people have been very interested in the feasibility of random 3-set formulas, for example. And this sounds like a...
I'm not so familiar with this.
Okay.
And well, the model that we are actually looking at, it's a very restricted model, and it's I mean, it would be nice to have some some connections with, but I'm not so sure.
Okay. Well, but this lot's easier. I mean, in terms of feasibility and feasibility, it's just a bunch of random linear equations, right? And whether they have a solution or not.
Yeah.
Well, it's known there too that there's a pretty sharp threshold, phase transition from in terms of the number of constraints, which is exactly so. There's an exactly corresponding. It's also called M in that literature, and as you increase the number of 3-set clauses, you make a very rapid transition, which will happen here. Okay, it's not because of this plot. It's because as you move most of the it's because of the math concentration of the Gaussian.
Yeah.
Here.
Yep.
All right.
Maybe we should talk about that.
Yeah, sure.
Right. So let's see. Okay. So this is for LP, and this is sort of known, and so we are sort of interested in semi-definite programming and what's happening there. So very okay. And one thing to actually one can actually see what's going on if we sort of restrict to the let's restrict to the plane and we have one constraint. So this is not only a toy example, but after all we will see that we can reduce the general problem to this two-dimensional setting. So it's sort of nice to have to see that actually we can understand what's going on for this EDS thing. So yeah, for n equal 2, and so we're in the plane and we have basically one constraint, and so well we take this basically standard normal vectors, but okay, so this is sort of not so nice to work. Let's say that instead we take the following picture. So let's say we maximize this V and subject to this WX. So and now we choose this W not according to the Gaussian distribution, but say on the unit circle uniform net random, right? And then we take the function that we want to maximize orthogonal to this constraint that we have, and well, and then we have two choices. We can either go, because this intersection is exactly 2 points, and then we can choose one of them with probability 1/2. Okay, so yeah, so okay, let's say that we want to consider this CP prime, right? And okay, now we can actually draw some pictures and see what's going on. So this little W gives us our affine line here in the two-dimensional space, and this V gives us our function. So if we have this situation, then this optimum lies here, and then you see if we rotate this in this direction, this goes to here, and you can imagine that if we rotate a little further, then we get an infeasibility, right? And so yeah, and okay, so let's put some notation to this. So let's say we have the cone C, and we have two rays. Say the left ray R1 and the right ray R2, and we have the dual cone down here. And so now we have two possibilities. So we have this W and V. They are form a right angle, and now we may have two orientations. So we have this orientation, or we may have this orientation, right? And so now the plot that you see here is sort of this is in well, this is when you consider where this vector V actually lies. So if V points, if V lies in this well in the cone C, then the value actually will be infinity, right? If you think about this, then we have this situation here, and if we put V in this direction, then we will actually have an unbounded outcome. If V lies in this half space, then we will actually have a bounded program, and the solution will be here on R2, and well, so I'm just showing you this picture to make clear that for the two-dimensional case, we actually know everything. All these probabilities, it's sort of easy to verify. I mean, it's really just two-dimensional thing, and everyone can verify this. All right, but now we're interested in, well, we're not interested in the case n equal 2 and m equal to 1, but we're interested in the general case. And so let me just put the result here, and then we can see how this is actually achieved. So assume that we have a Borel set M in Rn, and which is scaling invariant, so it's sort of like a conical set. So think about M being the set of rank R matrices in the set of symmetric matrices, right? And then we want to know, okay, what's the probability that the solution of this convex program lies in the set M? And it turns out that one can write this probability in terms of the so-called curvature measures, right? So I haven't explained what the curvature measures are, but this is what will come next. So this is sort of like to motivate have a look at the curvature measures, right? Okay, so what are these curvature measures? There are certain localization of intrinsic volumes. So just a short reminder what the intrinsic volumes were. And basically, we take a convex cone C, and then we get this tuple of positive numbers which form a discrete probability distribution. And if we have a polyhedral cone, then we have this nice characterization. So remember that choreographic F was the set of relative interiors of the faces of C, And so these relative interiors form a disjoint decomposition of the cone C. And then we have to find the projection onto C and this map D, which sort of, if you have a point X in the cone C, then this yields the dimension of the face where X actually lives in, right? And then we've seen that the jth intrinsic volume was basically the probability that if you choose a point P uniform or general on the unit sphere, or according to a standard Gaussian distribution, then the jth intrinsic volume is the probability that this composition D after the projection is just J. So we basically get this decomposition of the Euclidean space, and this gives us these probabilities, right? And okay, another way to write it is a sum. So we sum over all J-dimensional faces of the cone C, and then we ask about the probability that the projection lies in such a J-dimensional face. Okay, and now we want to localize this probability, and so the way to localize this is to actually take the intersection of F with a certain conical subset, and this is what we're going to do next. So let's make the following definition. So we define what we call the conic Borel sigma algebra, which consists of those Borel sets which are scaling invariant. So we only consider sort of conical subsets. And actually we have the following structure, which is hopefully gives some idea of what this look like. So if we have a conic subset, so we have some element of this conic Borel sigma algebra, then we actually can, it's enough to consider the intersection with the unit sphere, except that we don't know if we have the origin in the set or not. And in this way, we can actually get a disjoint decomposition of this conic sigma algebra in these two sets. So we have those sets which contain the origin and those sets which do not contain the origin, right? And both sets are, in a straightforward way, isomorphic to the Borel algebra of the unit sphere. So in a way, we have just two copies of the unit sphere, of the Borel algebra of the unit sphere, which sort of seems too overly complicated. But in fact, it's really very convenient to consider it in this conic setting. And we'll see later why this is actually very nice. So now we've defined this sigma algebra, and now we can define the curvature measures. Now the curvature measures are, well, there are valuations. There are measures on this conic sigma algebra, and here you see. Well, okay, so this is the definition for polyhedral cones. I should stress this point. So for polyhedral cones, we have basically the same definition as we had before for the jth intrinsic volume, but here we only take the intersection of the j-dimensional faces with this Borel set M. Right? In this way, we get a certain localization of the intrinsic volumes. And so one actually can verify that this gives a measure on this Borel algebra.
So I'm wondering why you call this curvature measure?
Well, yeah, if you recall the definition of the intrinsic volumes of smooth cones, so there we had the integral over the boundary, and then the integral was of the principal curvatures. Okay. And if you consider if you ask about the curvature measures of smooth cones, then you only have to take the intersection of the boundary with this Borel set M. And that's why they call it curvature measures. And so first obvious observation is that these are in fact localization of the intrinsic volume. So if you put here for the set M the cone C itself, then we regain the intrinsic volumes. And actually, if we have some set M, then we can also take the intersection of the set C. So it's actually a measure which is concentrated on the cone C. And this is later, well, it's not too important, but it's sort of, it's good to know this. And yeah, so this is also a nice observation. So if you have a decomposition of the cone C, then we actually get a decomposition of the jth intrinsic volume as the curvature measures in these pieces of the cone C. So if you think about the cone C being the set of positive semi-definite matrices, then you get a natural decomposition in the, say, rank R matrices. And then you see that you get a natural decomposition of the intrinsic volumes as the curvature measures of the rank R matrices.
So these really are measures.
Yeah, they're measures. And yeah, and then some special cases. So first of all, the nth intrinsic volume is now not the relative volume of C, well, C intersecting with the unit sphere, but well, the relative volume of this intersection with this M. And now this is actually, this looks very innocent, but this, well, for a long time this is, it was not clear how this phi 0 fits into this picture. But since we have used this conic sigma algebra, we actually get a very nice interpretation of phi 0 as a Dirac measure, a scaled Dirac measure. And yeah, and this is actually sort of, this convinced me that looking at this conic sigma algebra is actually the right way to look at these curvature measures. Okay, so yes. So another remark that these measures are actually weakly continuous. So if we take a sequence of convex cones which converge to a certain cone C, then also the intrinsic volumes, then also the curvature measures converge to the curvature measures of C. And so I've shown you the definition for the polyhedral cones, but actually this, I mean, if you believe this continuity, then this gives you also an extension to general cones. But actually, so phi j can be extended to non-polyhedral cones, but actually, if you really want to define it as we did before in the first talk, then you can actually do this. So you basically replace the tube of the whole cone by some local tube, and then you see that these curvature measures appear as certain coefficients of this volume formula. Right, now, okay, what's the kinematic formula? Let's say that we take a closed convex cone C and some Borel set M, some conic Borel set M, and let's say that M lies in C, so this is an assumption that we can make without any loss of generality. And now let's say that we take a uniformly random subspace of, say, codimension M, and we take the orthogonal projection on the subspace. Right? So imagine, recall that we said before that kinematic formula is basically you take some fixed set and some random set, and then you ask about, okay, what about the intersection, or what about the projection if you take a subspace? And right, and so now we get for this random projection of C on this subspace W the following. So the expected jth intrinsic volume of the projection, well, evaluated in the projection of this Borel set M, is just the jth intrinsic volume of C. So the way to visualize, sort of remember this is saying that, okay, if I have this intrinsic volume, then the projection basically cuts off the right tail, right? And this is actually a stronger statement because this is actually the statement about the curvature measures, right? I mean, yeah.
So M can be anything, doesn't have to be C.
Say it again?
So M can be anything, it doesn't have to be just the cone C.
Right, right. It has to be a conic Borel set.
Isn't this conflict? So if you put in all of C instead of M,
Yeah.
doesn't this conflict with the fact that they have to sum to 1?
No, because this only holds, that's a good point, because this only holds from 0 to n minus m minus 1. The rest, well, okay, you're actually right. So they have to sum up to 1. So what about the n minus m intrinsic volume? And well, this has to contain the right tail.
Okay, so everything is just stuck in the last one.
Yeah, exactly.
Okay, I see.
So they all get collapsed down to
Yes, yes.
So, so that, yeah, so you're drawing this like a spike here.
Yeah. That,
So everything stays the same and then everything else gets collapsed onto.
Right. I mean, the intrinsic volumes sum up to 1, so also the expectation has to sum up to 1, so this right tail gets sort of accumulated in the last.
So that's, I mean, it's sort of like a Dirac there.
Sort of, yeah.
I mean, it's all discrete anyway, so it's extras.
Okay, so yeah, and this is about random projections. And okay, now you can ask for what about the random intersection? And well, actually, you get quite similar formulas. Yeah, so but now you see that we get here this shift in the index. And okay, maybe don't worry too much about this formula. This is a very nice way to actually visualize this. So we have seen the projection cuts off the right tail, and in fact, the intersection just cuts off the left tail. Right? And this is actually how you can easily remember what's going on here for the expectation of the curvature measures. So yeah, okay. So this is nice, and so now the question: how can we apply this kinematic formula to solve our question about the probability, about the solution of a random convex program? And yeah, so right. So now how to apply this kinematic formula? And the idea is that we apply the kinematic formula twice. So first of all, we will see that we can actually reduce the general case that we have. So we have a convex cone, and then we have some affine subspace, and we can actually reduce this to the codimension 1 case. Right? And once we have assumed that we have the codimension 1, we can actually see that we can go one step further and apply the kinematic formula again, and then reduce everything to the case n equals 2. And for n equal 2, you've seen that you actually can see everything by just drawing some pictures, and then you get everything. So yeah, so this is the idea, but okay, let's make this precise. Well, we need to introduce some notation. So you recall that in our Convex program we had these affine inequalities, and say that W is now this linear subspace, so the linear part of this affine subspace, and the affine subspace, let's denote them by WF. And okay, now let's say that W tilde is the linear span of this affine space. So, right, in this way we get to the codimension 1 case. So, so now this is actually the linear space. So the WF is now an affine space inside this W tilde, but inside W tilde it has codimension 1, right? And okay, so the first application now of the kinematic formula says that okay, if we're basically looking at the intersection of the cone C with this WF, but actually we can first of all replace this cone C by the intersection of C with W tilde, and then then the ambient space is, say, W tilde, and we are in the codimension 1 case. Right? How this application actually works, then we will see this later, but let's say that we've done this first step, and then...
Can you explain that again? So why can you replace C with C intersection?
The point is that we want to choose these inequalities sort of uniform at random, right? So if you take the linear span W tilde, then this will be a uniformly random subspace, right? And so the kinematic formula says that the expectation of this intersection in a subspace, sort of, I mean, this what's going on for this intersection in expectation, and so the proof actually goes backwards. So this is sort of like let's take this as a motivation to the actual proof.
So the claim here is that inside W tilde WF is a uniformly random subspace of codimension 1.
Yeah, but not only that, also the subspace W tilde itself is a uniformly random subspace, right? Because it's defined by WF, and this is here we've chosen the
There's not a degree of freedom from the B that's not random.
Sorry? Yeah, the B are, I mean, you can, yeah, so the B are, they don't play too much role. So it's just that they're not allowed to be all zero, but so this doesn't change the fact that W tilde is actually a uniformly random subspace. Yeah. But maybe, okay, so the actual proof goes the other way around.
I'm confused about this. So
Yeah.
what is the dimension of W tilde?
W tilde has codimension m-1, right? So this W has m constraints, so the codimension is m. And now we take the affine space and the linear subspace. So W tilde is the dimension of W plus 1. And so the codimension is m-1 of W tilde. Okay. So yeah, but maybe that's, well, in the end we will actually see the argument in the right order, and then hopefully everything gets clear.
But then what have you written down there? I.e. codimension of W is equal to 1? Your last line?
Well,
Yeah,
the codimension of W inside W tilde.
Oh.
Sorry. Yeah, I should have written a W tilde down here to make this clear. All right. Okay, but so maybe let's just assume that we have codimension W. So we only have one constraint, let's say. Okay. So okay, let's. Now we have this affine space, but we can actually replace this affine space by saying, okay, let's take this all to say height 1. Right, so maybe let's just look at this picture. So our ambient space is W tilde, our linear space is W, and our affine space is somehow over here. And now we define this normalization WF naught. But actually, we only have to look at this small w, because now we can, since we are in a codimension 1 case, we can actually write this affine space in the form, okay, these are those x in W tilde which have a scalar product with little w equal to 1. Right, so now everything we have to look at is basically this scalar product with the W tilde. Okay? And so instead of looking at this convex program, we now consider the following convex program, say CP prime. Okay, so this is just a reformulation of these constraints. So well, we say that x should lie in the intersection of C with this linear subspace W tilde. And
so this is clear now. So you're saying you can replace the constraints with a single constraint by restricting the cone.
Right. Yeah. Yeah. So yeah, I think it gets clearer when the argument, when the full argument actually gets revealed. And okay, now to make things even easier, let's say that we replace this linear functional z by this projection, right? So well, we're maximizing this functional subject to this affine space, but w is the normal direction of this affine space, and so we can project everything to this space little w. It just makes things a little easier to work with. All right, but now, okay, so now there's one very simple but quite essential observation that we make. So if you look at this convex program, then everything we actually look at is the scalar product with little v and the scalar product with little w, right? And so now, okay, if we only consider the scalar product, we can actually first project onto this two-dimensional space spanned by v and w, and then look at the projection. We only look at the scalar product anyway, right? We don't lose any information in this step. So this is the second application of the kinematic formula. So instead of looking at this program CP prime, we look at the projection onto this two-dimensional subspace L, and then we want to solve this convex program, right? So we have the same linear function v and the same constraint, but now we restrict ourselves to x lying in the projection of this intersection of C onto the two-dimensional space L. And now, okay, so this CP double prime is now actually a two-dimensional convex program, and we have seen that, okay, there we see all these probabilities, and there's no problem at all to actually solve this two-dimensional question. And yeah, and okay, so for this transfer, one actually needs a little lemma which says that the solution of this program CB prime, this lies in a certain set M, if and only if the solution of CB double prime lies in the projection of this set on L. Right? So this is an easy lemma, but it's this is sort of like the link between these two sets. Okay, but now we have everything, so let's see the full argument in the right order. Right? So we start out with this probability that we want to solve. So the probability where we choose the Fn constraints. Okay, so sorry, I've written this B1 to Bm, but these are fixed. Forget about these. Sorry. Right, but now we change our probability model. Then we say that, okay, first we choose this W tilde uniformly at random, and then we choose this V and W at random, and then we solve this CP prime. Well, and then we ask about the solution of CP prime, and this should lie in the intersection of M with W tilde. Right? And okay, so, but then we can apply the lemma and go one step further by saying that, okay, instead of choosing this W tilde, I choose this W tilde and the subspace L, and then inside L I choose V and W, and then I look at the Convex program CP double prime, which is a two-dimensional thing, and ask that the solution should lie in the projection of this intersection of M with W tilde. Right? Okay, but as I said, so if you only consider this part of the equation, then this is a two-dimensional situation, and there we can actually very easily verify that what we have over here is just the first intrinsic volume, the first curvature measure of this projection, and we get this projection of this intersection of M with W tilde. Right? So this, up to this point, this was just some geometric reformulation of this probability that we're starting with. But now, okay, we're actually in a very nice situation, because now, well, now we have, let's say we fix W tilde and only take this subspace L uniformly at random, but then we get here the projection on a two-dimensional space, and we ask about the first curvature measure, and then we can apply the kinematic formula, which says that, okay, this expectation is just the expectation of the first curvature measure of these guys. Right? And now we see, okay, now here I choose W tilde uniform at random, so I can apply this kinematic formula again. And then we see that, okay, we get the nth curvature measure of C in M. Right? And now you can see that this was sort of like the first step that we did to reduce to the codimension 1 case. It's actually the last step if you write out the argument in full order, in the right order. Yeah, well, and that's it. So you see that the main step was sort of like a geometric reduction to a certain situation where we can apply the kinematic formula, and then the kinematic formula just puts out the answer. Okay, and so I said before that the probability that the Convex program is infeasible or is unbounded. This is slightly easier. So there we can, then we only have to use the kinematic formula once. But once you have seen this argument, and you can actually, well, you get the other cases as well. So this is all. But okay, but this is now much more information. So this actually lets us answer the question. So what's the probability that a random semi-definite program has rank R? Its solution has rank R. Right. So okay, now I've talked about the kinematic formulas, but actually, I think for a good understanding of these formulas, it's actually essential to understand what these support measures are. So let me say a few words about the support measures, because I think it really shows what these kinematic formulas in the spherical cases are. And because it actually turns out that there's one formula which actually gives not only the intersection formula, but also the projection formula. It's just, you know, these are specialization of one very general formula. Okay, so what are the support measures? Sorry, I just maybe should go one step back. the curvature measures were localizations of the intrinsic volumes where we said, okay, we project onto the cone and then we want to restrict the domain where we're landing, right? But this breaks the duality, right? We treat the primal cone differently than we treat the dual cone. And so this way we lose the duality. And the support measures is some localization where you can interpret this as a primal dual localization. So you not only restrict where you land on the primal cone, but you also restrict how you land on the dual cone. And this way you regain the duality and you get a very nice picture of really what's going on. This is sort of like the main idea behind the support measures. And well, to define these for polyhedral cones, I first need to remind everybody on the phase duality for polyhedral cones. So if C is a polyhedral cone, then we have this calligraphic F and calligraphic Fj to denote the phases, say of dimension J. And if you consider the phases of the dual cone, then, well, we can do this. Let's say we have this calligraphic F perp and Fj. And so that there's a very classical result saying, excuse me, that we have a bijection between the j-dimensional phases of the primal cone and the n-j-dimensional phases of the dual cone, right? And this bijection goes exactly like this. So if you have a phase F, then the dual phase is just the intersection of the dual cone with the orthogonal complement of the phase F, right? Okay, so this is a very nice bijection between the phases of the primal and the dual cone. And so now we want to localize the intrinsic volumes in the primal dual way. So we need to take extend our Borel algebra. So let's say we consider the Borel algebra on this direct product of Rn times Rn. And now we consider these what we call the biconic sets. Sorry, I should just go to the definition. So we now we consider those subsets of Rn times Rn, which are scaling invariant not not only for the first part, but so we want to scale the first components and we want to scale the second components, right? And we call this the biconic sigma algebra. So this is sort of maybe you can imagine that. Okay, so some elements of this Borel algebra are direct products of elements in the conic sigma algebra, for instance, right? But there are some more in there. And well, basically the main part of the biconic sigma algebra is the Borel algebra of the direct product of two unit spheres. So maybe you can think of this as the Borel algebra of a direct product of two unit spheres, which sort of gives. But it's very useful to consider this in this conic setting. Okay, now, well, as I've tried to explain before, now instead of just considering the projection onto the primal cone, we consider both the projection on the primal cone and the projection on the dual cone, right? And now you can maybe you can imagine what the definition looks like. So you see that we basically get the same definition as before, but now we say that, okay, not only the projection onto the primal cone, but the projection onto the primal cone and the projection on the dual cone needs to lie not only in this direct product of the faces, but this intersected with this Borel set calligraphic M. And okay, so now you can imagine. Now you see that we don't treat the primal and the dual cone differently anymore. We treat them just the same, and in this way we regain the duality, right? Which is sort of the yeah.
I'm puzzled why there are not two indices here. Is it not conceivable that if you have a point and you project onto these two cones, that you might land on faces of, you know, not dimension j and n minus j, or do you always are you always guaranteed to land?
Yeah, it is true. So, this is one. Yeah, I probably should have written this. So, if you project onto the primal and the dual cone at the same time, then you will lie in the j-dimensional phase, and you will lie for the dual phase in the n minus j dimension.
That's guaranteed.
Yeah, for polyhedral cones. I'm only talking about polyhedral cones at this point.
I mean, remember that that a cone induces an orthogonal decomposition of the vector, so this picture is
Right.
really accurate.
Okay, and in this way we get this nice definition of the support measures. Again, only for the polynomial cones, but the same, the same remarks apply to this case. So, right, I think I've written this down. So first of all, we again get a refinement of the curvature measure. So if we consider biconic sets of this form, so M direct product with C perp, then we regain the curvature measures. And not only that, so we not only can get back the curvature measures of the primal cone, at the same time we also get a refinement of the curvature measures of the dual cone. Right? So before, I mean, these were before just two, they were not connected, but so through the support measures, they're now, well, there are some, just some specialization of this. And this makes the theory very elegant. And and then again, as I said before, these are local measures. So instead of considering any biconic set, we can always intersect with this. So these are actually measures which are concentrated on this direct product of C with the dual cone C. And this is the duality of the support measures. So this M star is just flipping the components of these two sets. And then, okay, if we consider the support measures of the dual cone, then it's just saying that we're considering the n minus j support measures of the primal cone if we replace M by this M star, if we change the components. Because we've treated the primal and the dual cone in just the same way. And okay, again, theta j is weakly continuous and thus can be extended to non-periodic cones. And well, again, as I said before, if you want to have some definitions as we have had for intrinsic volumes, you can again consider a certain tube formula for local tubes around the cones, and then these support measures will appear in the corresponding tube formula. All right, so so these are the support measures, and okay, a very nice thing to point out is that we have certain lattice structures in there. So the set of cones is it doesn't have too much structure, but it has some. And so it's I think it's very to point this out. So let's say that we denote the set of closed convex cones by calligraphic C, and then we define the negation, the wedge operator and the V operator in the following form. So, well, the negation is just taking the dual cone. This makes totally sense. Well, the AND operator is now just taking the intersection, and well, the OR operator is now taking the Minkowski addition. And well, actually, one has to take the closure of this set because it's not necessarily guaranteed that this is again closed, but I mean this is a very small. It's just a subroutine, just a nice subroutine. Okay, and then we have these, these identities that are easily checked.
The V operator, is that also a convex cone? C1?
Yeah. So these are operators on the set of closed convex cones.
I understand. So that your notation means, so you're really computing the convex cone generated by C1, C2?
Yes. Right. And this is the dual set. So we actually do I have this? No, I don't. Let me write it here. So we actually have a De Morgan's law, saying that if you take the negation of, say, C intersected with D, then we actually get minus C wedge minus D, which says that okay, the dual cone of the intersection is just the dual cone, the Minkowski sum of the dual cones, and then the closure. So this is very valuable if you actually want to do the computation. It sort of gives you some nice formulas that you can actually work with. And and we also have some further identity. I should point out that at this point it's really essential that we take what some people prefer to call the polar cone. So we actually take the cone which lies downwards and not upwards, because this way we actually get this identity. You wouldn't get that if you get the upper terms. Right. And now the effect is so that this set with these operators define this what's called an ortho-complemented lattice. It's not a very strong structure, but this is the structure that we have. If we restrict ourselves to linear subspaces, then we have what's called the modular law. So we have some more structures, and if we restrict ourselves to say to the case n equal to 1, then we actually get the Boolean algebra. So it's sort of, I mean, we allow more sets, but then we lose some structure. It makes sense, right? But okay, this is the structure that we actually have.
Which is weaker than a distributed. How does this relate to being a distributed lattice?
I'm not so firm in this, but so I've checked the axioms, and so I've come up with ortho-complemented lattice to be sort of like the strongest thing that you can actually prove. Yeah, so it's not too strong, but so we actually have this complement, and these are the axioms I think for actually having an ortho-complemented lattice. All right, so these are this is the structure for the set of closed convex cones. Now we also have some structure at least for the biconic sigma algebra, and let me also mention this. So okay, so some notation. So let's say that m, index x is now sort of the right fiber. So a set of all v such that x v lies in m, and so we also have the left fiber. And now we can define again these operators. So the minus operator is now taking, just exchanging the components, and well, the intersection is now. So you need to read it in the right way. So this just means that we're taking the intersection in the first component while taking the sum in the second component. So this looks a bit technical, but this is the basic idea behind this, that if you want to take the intersection, then we take the intersection at the primer in the left component and the sum in the right component. And this, if you write down the formulas for this, then you can write it this way.
Do you have issues with duality when you do just the right-hand sum, or do you have to take a closure?
I don't think I have to take the closure, no. But so this is okay. So I should point out that this is not a very strong structure, and it's not even a lattice. So it is really it's a very weak structure, but still, what we have is the Morgan's law in a way. So we actually have these nice identities, and this is sort of, for us it is enough to work with in sort of an algebraic way. Okay, so these are the lattice structures that I just wanted to show you, and so this way we can actually state the kinematic formula for the support measures in a very nice form, which just sort of makes things very standing out with what's going on. Okay, so the theorem is the following. So this is Dasauer's kinematic formula, and it says the following. Let's say we take two closed convex cones C and D, and we take two biconic sets, and now we assume that M lies in the product C with C printer, and N in the product of D with the dual of D. Right, and now we have this this nice result that says that if you take a uniformly random element of the orthogonal group, and we take we take the AND operator of this CM and DN, and ask about the J support measure, then this actually has the form of a convolution. And this is sort of and from this is sort of the central kinematic formula in the spherical case, because if you want to specialize this to the kinematic formula as that I've shown you before, this intersection and the project onto linear subspaces, you can derive them from this formula by just intersecting. Just specializing the set M that we have here. And it actually, so this is the formula for the AND operator. We may as well write it in form of the dual operator, but so these two are actually equivalent in a straightforward way. because that's why I've shown you this formulas before. We have the De Morgan's law for these two structures, and actually it's just it's just a matter of writing this down to see that these two formulas are actually just one formula. So this way we get one kinematic formula that actually gives us all the remaining things. And this is very special. I should point it out. This is really special to the spherical viewpoint. We don't have this in the Euclidean case. And this is really just makes the theory very, very elegant in a spherical case. Okay, so yeah. So let's wrap things up. What we've seen before is that if we ask about the question about the expected solution of a convex program, then we have seen that it all boils down to the curvature measures of the specific cones. Right? And now we want to specialize to the cones of positive semidefinite matrices. And so now the question is, what are the curvature measures of this cone, this particular cone? And so I will end up this talk with some formulas for these volumes, for these curvature measures.
Before you do that, can I ask, so what classes of cones or are these measures, have they been computed for?
Well, yeah, that's a good point. So, so right now, I mean, we have this examples that I've shown you before. We have this, I mean, positive orthant, of course. We have the circular cones, and now we also have the symmetric cones. And I would say that symmetric cones are sort of like the most elaborate example that we have right now. But this is like the major question, how to actually treat this. And I will come to this question back in the third talk, because this is sort of the major issue with the whole theory to how to actually handle the intrinsic volumes and how to handle the curvature measures. But this is the main one. Okay, so let's introduce some notation. Just to be complete, let's not only talk about the real numbers, but also about the complex and quaternion. If you don't like this, then just think about the real cases. But the reason I show you because we end up with some formulas that we cannot completely solve. And I have the impression that it's the easiest way to first try to solve this for the complex numbers. And well, once we have the complex numbers, it's no increase of difficulty if you also cover the quaternion case. So it's sort of and okay, let's say that beta indicates the ground field. So if beta is 1, then we are talking about the real numbers. It's beta is equal to 2, then the complex numbers, and 4 it's the quaternion numbers. And right, if you maybe just think about beta equal to 1 in the real case, which is well like this. So the stage of semi-definite programming is that we consider the set of symmetric matrices, or in the case of complex and quaternion case, we consider the set of Hermitian matrices, right? And so this is a linear subspace of the space of matrices. And if we want to compute the dimension, then let's look at the right-hand side. So the diagonal elements need to be real elements, right? And then we have some symmetry. So let's say we only consider the upper triangular part. And these are free, and okay, so this way we add up with a dimension of n, where n is the diagonal elements, and then we have beta times n over 2 for the off-diagonal elements. Right? So this is just a real vector space in the set of n times n matrices, and this is the ambient space, right? And well, this is the ambient space, and so we also have a scalar product, which is usually denoted by this bullet. But this is just the usual scalar product, reduced to this linear subspace, right? And then okay, so now the normal distribution on this subspace has a fancy name. It's called the Gaussian orthogonal ensemble in the real case. It's called the Gaussian unitary or symplectic ensemble in the complex. But it's just a naming. It's just so these are just names for the normal distribution. So we are exactly in the same situation that we had before, but now it's called, well, let's say that we have the G beta E ensemble. Right? Now the reference cone is, of course, the set of positive semi-definite matrices, right? And now we have this natural decomposition according to the rank, right? And okay, so the semi-definite programming now reads in the following way. We have as inputs these matrices and some real numbers, and then, well, the problem is just before, we have linear functional that we want to maximize and some linear constraint, and this positive semi-definite, this constraint, this convex constraint. Okay, and the random SDP is now as before. We choose these inputs to be normally distributed, and these inputs are some fixed constant. Right, and now a corollary of our general result that we had before is now that the probability that the solution of a random SDP has rank R is just the nth curvature measure of this cone in the set of rank R matrices. Okay, and well, I should mention the Pataki inequalities, which say that the rank cannot be rank cannot be arbitrary, but with probability 1. The rank satisfies these inequalities. They are called the Pataki inequalities. So this was known before, but now the question is, well, in this interval, how is the rank distributed? And this is a question that couldn't be answered before. So now we can at least give a partial answer to this.
What is D?
Sorry, B is
D.
D is the dimension. D is the dimension of this.
Oh, this space.
Oops, yeah, okay. And now, remember that the linear program is connected with a binomial distribution, and I like to think of this in terms of having a different distribution for semi-definite programming. So semi-definite programming has a different distribution. And this distribution has a finer structure according to the rank. Right? So this is sort of like the general picture that you have in mind. And again, I mean, this is, as we had before, so with very high probability we are actually infeasible or unbounded, and so the random model is not that useful. But anyway, it's the simplest model that you can imagine. So it's natural to start at this point. Okay, now what are the formulas for the curvature measures? And okay, let's say we denote the fundamental determinant by delta of C, and so now there's a general. Just showing you this, which is called Mentas integral. So if you have a Gaussian density on Rn, and you want to compute the expectation of this fundament, then we have a closed formula for this, and this is formed by Meta, I think in the 60s or so. And so this is known, right? Okay, but now we want to, so now we start at this fundamental determinant, and we get a certain decomposition of this. So let's say that we take an R between 0 and n, and we decompose our vector z by saying, okay, the first R elements we call x, and the last n minus R elements we call y. And then it turns out that the fundamental determinant raised to the power beta decomposes in this form. So we have the fundamental determinant on x, determined on y, and then some mixed terms. And so this f beta k x of y is a bisymmetric polynomial in x and y. So, well, let me not go into too much detail here. It's just to show that this decomposes in this way. Right? And so now remember that the meta integral was giving a result for the integral of this form. That we take the fundament and then we integrate with respect to some Gaussian measure. And let's say now we define the same, almost the same integral. So there are two important differences. So instead of taking the integral over whole Rn, we only consider the integration over the positive orthant. And now we've replaced this fundamental determinant by this decomposed fundamental determinant. Right? And let's say that we denote these integrals by j beta of n R and k. And so n is the format, R is sort of the rank, and k is now between 0 and beta R times n minus R. Okay, now finally we get to the formula for the curvature measures. All right, and then we say that these are 0 if k is outside of this interval. Okay, and now finally the theorem which says that the curvature measures of the cone of positive semi-definite matrices is basically this J integral. Divided by the meta integral, but these are just some normalizing constants. Right, so this J integral is actually giving us the curvature measures of this.
Can
cone.
you compute that? I mean,
we will come to this. So this is the major point. We cannot totally solve this right now, but it's sort of, it's an ongoing thing.
For beta equal to 2, you can compute?
Yeah, I showed it. And okay, so we can write this as an integral, but then we can also write it as an expectation. So maybe this is also a nice way to look at it. So if we say that we take A from the Gaussian beta ensemble, and then okay, so we need A to be positive semi-definite, so we get these indicator functions here, and then we basically get the expectation of this F function. And this F function, these were the sort of the mixed terms of the fundamental determinant, right? And so this is just another way to write this integral. It's just, I don't know, and you can see that these constants also have some, binomial structure in a certain way. Okay, but now, so now we have these formulas and what to do with this. So we can solve this for, it looks like a big table, but actually we can solve this up to 3 by 3 matrices. But this is as far as we can go right now. So it's but you can see it. It's if you just look at it from far away, it doesn't look too ugly, right? These are really nice things. And okay, this is basically rational if we take the inverse of pi to this, so it's not too bad. So and actually, when I did this computation, as soon as I made some mistakes. I got really ugly formulas. But when I finally erased all the mistakes that I made, I really got this nice structure. So there really seems to be some structure behind that we haven't discovered yet. So it's just a way that we haven't. It's not the story is not complete yet.
But it looks like when beta is 1 is when you get irrational, right? And when beta is 2 and 4, you don't get anything irrational.
Yeah, right. So and that's why I think that it's probably easiest, but it's probably the best thing first to consider the complex case, because I think this should be easiest to handle. Right. Okay, but we also did some. I also did some numerical computations. So okay, so these are the exact. These are the exact values, but also I did some numerical computations for the 4 by 4, 5 by 5, and 6 by 6 matrices, and so at least you can see a certain thing that will come up in the last talk, that this actually looks like a log concave probability distribution, right? And so if you take the logarithm of these, then you see that you get a concave. So this is a numerical. You can see that I really did a numerical procedure to get these numbers. But okay, so this will come in the last talk. That this actually looks like a log concave sequence, and this is actually a conjecture for the general case. And this, right? But this will come up in the last talk. So.
But what would be the significance of that?
Well, the significance would be that in a way that, okay, log concavity alone is maybe not enough, but it would in some way imply that you get a very sharp peak if you look in high dimensions, right? And this would be like a general threshold phenomenon for basically any high dimensional cone. And this is really, this.
So one way of thinking about this is that if you look at the orthon, for example, and you see that these intrinsic volumes are very sharply peaked around half the dimension. In some sense, the orthon looks like an object that's n over 2-dimensional. And you see the same phenomenon here for the semi-definite cone. It looks somehow like an object that's half-dimensional.
Right.
And they're relatively simple ways of identifying where the peak is, just using the fact that the cones are self-dual.
Right, I guess if you do like Gordon's escape from mesh type business, you can get those thresholds.
It's not hard to argue even Gaussian widths. The peak has to be halfway. But you don't know about the rest of it, how fast it drops off, or anything else.
Right. So having
the
asymptotic formula
care
for
about,
this.
the whole thing. You might just care about how it drops off or something like that.
So getting asymptotic formulas for these curvature measures, it's really, that's an open project, but it still needs to be done. Right. So at this point, maybe just let me first, let me because we've seen a few concepts in this talk. So let's say, so we started at the question of the expected rank of the solution of a random SCP, and this led us to three things. So we had these curvature measures, and we had these kinematic formulas, and then finally we had some explicit formulas for the symmetric cones, right? And to apply the kinematic formulas, we actually had this nice reduction to the two-dimensional case, which sort of gave us a certain answer to this question that we were starting out at the beginning. And then, okay, then we see that to actually understand the curvature measures in the kinematic formulas, it's, I would say, really essential to know about the support measures, because this is sort of, this really, for me, this lies at the heart of the whole theory. And yeah, open questions, of course, can be solved with change. This is sort of okay. And yeah, let's stop here and then.
So, any more questions for Dennis?
I don't know if it's a question, but if you look at, so if you're interested in the asymptotes, so for beta equal to 2, where you typically have the square of a van der Monde, when people have looked at, say, asymptotes of that, a useful direction, you may already know this, is to go through this orthogonal polynomial route, and then there's tons of stuff that are known about asymptotes of those, and so that might give some help.
Yeah, that's okay, but it's true. So I've recognized this, but I haven't dived into this theory yet. So it's, yeah. But I should mention what is known is for the beta equal to 1 case. So about the probability that if you take a random matrix from the Gaussian orthogonal ensemble, what's the probability that you have a positive semi-definite matrices? And the asymptotics for this probability are known, which is sort of the largest intrinsic volume. And so this is also one direction that it's probably worth looking at to maybe extend this to the other intrinsic volumes. Right.
So Dennis has one more talk in this lecture, which will be Thursday afternoon, same time, same place. And until then, let's thank him one more time.